Meteorites have been falling to Earth since the beginning of our solar system. Most people know their destructive qualities, but many do not realize their possible role in helping create life on our planet. It is known that the Earth experienced a period of heavy bombardment caused by Jupiter's migration to its current position in the solar system. Carbonaceous chondrites, a type of meteorite such as the Murchison meteorite of 1969, have fallen to Earth where they've been collected and tested for their composition, yielding the same result. These meteorites contain organic molecules necessary for life. Amino acids, alcohols, aldehydes, ketones, amines, pyrimidines, and purines have all been found to be components of these meteorites. Though these discoveries have been made, there are still doubts about the origins of these organic molecules in the meteorites, as they could have been incorporated through contamination from the impact. Our mission hopes to rid any doubts about the origin of these organic molecules in these meteorites by actually going and collecting them directly from the source, the asteroid belt. Using technology currently being created for the Asteroid redirect mission by NASA, we plan to build our own armed spacecraft to go and collect an identified ideal asteroid from the asteroid belt. 20 asteroids, 8 meters in diameter, have already been identified through the Near-Earth Object Program by NASA as candidates for this form of retrieval. Of these 20, one will be selected that has the most convenient orbit to intercept and is in a relatively safe section of the belt without a high density of asteroids to increase the odds of successful retrieval. The armed spacecraft will reach its target asteroid through the use of gravitational assistance from the Moon, as well as a newly developed engine called a Solar Electric Propulsion Engine. SEP engines utilize solar energy from solar arrays to create electricity, using this electricity to ionize and accelerate propellant to produce thrust. Through this method, less fuel is required and reduces the weight of the spacecraft by 20 to 50%, reducing launch costs as well as providing thrust over longer durations, making it ideal for deep space missions such as this. Once the spacecraft has reached its target asteroid, it will capture it in an inflatable bag system that can enclose the asteroid where it will be taken back to a stable orbit around the Moon for storage. The orbit of the asteroid will be stable for hundreds of years, and if it begins to move towards Earth, the asteroid is small enough to burn up in the Earth's atmosphere, posing no possible threat. While the asteroid is in its stable orbit, a manned mission aboard an Orion spacecraft, developed by NASA, will use assistance from the Moon's gravity to travel to and dock with the armed spacecraft, allowing for spacewalks on the asteroid to collect samples for testing. Once collected, these samples will be brought back to Earth where they can be tested using high-performance liquid chromatography under sterile conditions to identify organic molecules in the samples. If racemic mixtures of these organic molecules are found, it indicates that these molecules were produced not on Earth, but during the creation of these asteroids. Based on NASA's proposed budget for their mission, we would require $2.5 billion to research, develop, and test the new technology required, as well as costs for the launches for the 2 spacecrafts and compensation for the scientists and engineers working on this mission. Through these experiments, strong evidence supporting planet seeding can be obtained and can help increase the chance of success of future missions to find life on other planets by searching for planets that have had histories like our own.